the square root function. So let's sketch the function f of x equals the square root of x. So this function says whatever the input is, take the square root of the input. Now it's often a good idea to start off these sorts of exercises with a table. And I'll do that. And now I've done this many times before, so I'm going to say let's use these values for the table. -1, 0, 1, 2, 4, 6, and 9. So these are my inputs. Now let's go through the inputs and let's decide on what the output should be for this function. If the input is -1, the output, oh wait a second, the square root of -1 is not real. So this is a bad input. Okay, what about 0? Can we take the square root of 0? Yes, absolutely. The square root of 0 is 0. Okay, what about 1? The square root of 1 is 1. 2. The square root of 2, we can take the square root of 2. It's not such a nice number, but we can. If we use a calculator, we find that the square root of 2 is about 1.4. The square root of 4 is 2. The square root of 6. Now again, this is not a nice number, but again, we could use a calculator to find that the square root of 6 is about 2.4. And then finally, for 9, the square root of 9 is 3. So now taking these points and plotting them, now we saw that we could not put we couldn't get an output for this input. And in fact, we could not get an output for any input that's less than 0. So in a sense, what this tells us is this graph has a stopping point. And in this case, it's when x is 0. It's the stopping point in the sense that we cannot go any further to the left on this graph than when x equals 0. So we will simply draw this curve, which goes from 0, 0, and through these points. We'll just try and draw a nice smooth curve. Now the next nice point would be 16, 4, which would be like out here somewhere. So after 9, 3 here, it doesn't shoot way up, and in fact what it does is it just slowly increases. Okay. Now, when dealing with square root functions, it is important to understand the domain of the square root function. So what we can see from this graph and what we kind of talked about on the table, we can say that the domain of this function is the set of numbers x such that x is greater than or equal to 0. Basically what we're saying here is we can't put negative numbers into this function. Now of course we've learned that another way to write this is bracket 0, comma, infinity. Alright, either one is acceptable. If I ask you to determine the domain of a function and you write it in the set builder notation or intervals, I will accept it. Let's look at another case. What if we had the square root, our function is now defined as square root of x plus 2. Well, again, I've done this before, so I'm going to set up the table for you, and I'm going to choose these values. -3, -2, -1, 0, 2, 4, and 7. You might say, well, gosh, Joel, why did you choose those values? Well, I know what's going to happen. I know that -2 is an important input because it zeroes out the inside. It zeroes out the inside. Now what about -3? Well, if I put -3 in, -3 plus 1 is -1, and the square root of -1, wait a second, we saw this earlier, the square root of -1 is bad, right? What about if I put in -2? Well, -2 plus 2 is 0, and the square root of 0 is 0. If I put in -1, -1 plus 2 is +1, and the square root of 1 is 1. If I put in 0, 0 plus 2 is 2, the square root of 2 is about 1.4. Putting in 2 plus 2 is 4, the square root of 4 is 2. Putting in 4. 4 plus 2 is 6. The square root of 6 is about 2.4. And finally, putting in 7. 7 plus 2 is 9, and the square root of 9 is 3. So I chose these inputs to make the outputs the same as the previous exercise, to kind of show you something. It's a shift. We've shifted all of these inputs left 2 units. The outputs didn't change. The inputs, in a sense, got shifted left 2 units. And from what we see on the graph by plotting points, we see that we had that same shape, right? These are the same 6 points, that have all been shifted left 2 units. Again, drawing the curve, same basic curve, shifted left 2 units. What's the domain of this function? Well, again, looking at the graph, and looking at the table of values, we could say that the domain is the set of numbers x such that x is greater than or equal to -2. Or, of course, bracket -2 comma infinity. Let's just go ahead and let's use our calculator real quick. Now let's verify this graph. Alright, so going to our y equals screen, and let's see, second square root x variable plus 2, close the quantity, and let's look at this on the standard window. So I'm going to hit zoom 6 for the standard window, and I see that same basic graph, and notice it does appear to go through -2, 0. And we could trace a couple points here, like for example, let's trace 7. So trace 7, enter, and we see that it goes through the point 7, 3. Let's talk a little bit more about the domain of a square root function. So we saw that the domain of the basic function, f of x equals square root of x, is set of x such that x is greater than or equal to 0. And we saw that the domain of f of x equals the square root of x plus 2 is the set of x such that x is greater than or equal to -2. And basically a question that we might ask is, could we determine the domain without looking at a graph or even a table of values? And the answer is yes, we can. All we need is just a little bit of understanding and a little bit of algebra. We want the square root to be defined. And if the square root is defined, then its inside must be greater than or equal to 0. So we say that since the square root is to be defined, the argument of the function, the inside, must be greater than or equal to 0. So if we were to look at this function, f of x equals the square root of x plus 2, we could say that we need x plus 2 to be greater than or equal to 0. Solving this inequality, x must be greater than or equal to -2. So the domain is the set of x such that x is greater than or equal to -2. It's not so bad. So let's look at a couple more radical functions. I'll work through this one with you. Let's determine the domain of f of x equals the square root of 2x minus 10. Alright, again, this is a square root function, and we want it to be defined, so we need 2x minus 10 to be greater than or equal to 0. Solving this linear inequality, we add 10 to both sides and divide by 2, and x is greater than or equal to 5. So what this tells us is the domain of this function is the set of x such that x is greater than or equal to 5, or in interval notation, bracket 5 comma infinity. Alright, here's one for you to try. Determine the domain of f of x equals the square root of -3x minus 12. Be careful of that -3. Now would be a good time to pause. For this to be defined, negative 3x minus 12 must be greater than or equal to 0. Adding 12 to both sides and dividing by negative 3. Now remember, when we have an inequality and we divide through by a negative number, we must flip the symbol of inequality. So this tells us that the domain is the set of x such that x is less than or equal to negative 4. If we wanted interval notation, we would have to say parenthesis negative infinity, comma negative 4, bracket. Let's just go ahead and let's verify this last one on the calculator. So let's look at y equals the square root of, let's see, negative 3x subtract 12. Let's close the parenthesis and let's graph it. We're already in the standard window, so let's just hit the graph. And notice that this one sort of opens, or is going, it starts from the left and stops at negative 4. It goes as far as we want to the left up to negative 4 and stops at negative 4. Alright, now that we've discussed the domain of square root functions, let's look at the cube root function real quick. So again, our goal is to sketch f of x is the cube root of x. And again, I've done this several times before, so here's a good table to use with inputs of negative 8, negative 4, negative 1, 0, 1, 4, and 8. Alright, so if our input is negative 8, the output would be the cube root of negative 8, which is negative 2. Oh, remember, for cube roots, we can take the cube root of a negative number. Similarly, for negative 4, the output is approximately negative 1.6. When our input's negative 1, the output is negative 1. Alright, because negative 1 cubed is negative 1. 0, 0. When the input is 1, the output is 1. When the input is 4, the output is 1.6. And when the input is 8, the output is 2. Plotting those points on the grid. Alright, so this curve can go further to the left, and it will go further to the right. Because remember, we can take the cube root of negative numbers and positive numbers. Now, what happens after the points that we plotted? Now again, I mean, the question is, does it go way up, or does it increase smoothly? Well, the next nice point would be 27, 3. Well, if here's 10, then 27, 3 would be way out here somewhere. So we see we have a nice smooth increase, a slow increase. It doesn't jump up rapidly. And the same thing will happen over to the left. So drawing the smooth curve through those points, here's what the cube root function looks like graphically. What about the domain of this function? Are there any restrictions on it? Are there any bad numbers for this function? We found out that we could put anything into this function. So the domain is the set of all real numbers. Or in interval notation, parenthesis negative infinity, comma infinity, parenthesis.